And so far we have done is saying we take the free body diagrams, and on the free body diagrams we perform the static equilibrium. And for these two-dimensional problems, basically at most 3 equations: force equilibrium in x direction, force equilibrium in y directions, and then the moment about any point. So 3 equations at most. And I can tell you, for sometimes, if a problem is over-constrained, that means it puts more constraints than necessary to keep the static equilibrium. Once the system has been over-constrained, then very likely, I can tell you, is always the static equilibrium equations, pushing 3 equations won't be enough to solve for the problem. Again, for over-constrained problems, we need more information to help us. And so for those kind of the over-constrained problems, then we just define the static indeterminate problems. And for every single chapter, there's a few kinds of artificially designed and for exercise, for these problems. So I do my best to try to organize at least in this chapter, there's 4 types of the problems I've seen in the homeworks, in the exercise, and here I just do it. But I can tell you there's so many kinds of the indeterminate problems, and there's no kind of the template or no platform for these. So basically the learning objective in these sections is to try to, for yourself, accumulate the thinking process, the right thinking process, and then to approach the different type of the problems, because I couldn't give you too many things. The first one is this, a bar, and that has been constrained at both sides, and that is the typical examples of an over-constrained problem, because from here you can see if we put a constraint on one side only, this system can be reaching the static equilibrium. Okay, and why we want to get more additional constraint? Of course, there's some other design considerations which are beyond the scope of our class. They do have something, so that's one thing. The other one is this example, this is a gap. And if the force is, if the force would be small enough, then the deformation at this end wouldn't touch the wall. So the problem would be equivalent to is our traditional the determinate problems. However, if the force is big enough to push this end to not only touch but trying to push the wall, then this problem, once the gap is closed, then the problem will become like this. Okay. And this one is about composite materials. For example, if we consider 2 layers on the top and the bottom layers, they have a different cross-section area and they have a different Young's modulus. And this plate is we call the solid plate, and this plate is doing nothing but just to try to redistribute the loading not evenly in some way to each of these materials. So in this way, the force will be trying to compress the whole thing in the same way, and then again, this has more information, more unknowns than needed if we try to use the static equilibrium, then this problem wouldn't be sufficient to solve for. So in this way, we have to additional information. The last one is called the level. So this is a solid object, and basically no deformation, only responsible for the loading transformation or connection. And 1, 2, 3 wires are elastic, which means they are deformable. And for this one, basically the level originally as a straight line. After deformation of the 3 wires, these must remain as a straight line. So this is provide us the kind of similarity for the displacement at each end of the wire. So this is the 4th type of the compatibility equation, the 4th type of the indeterminate problems in these chapters. The common features of those indeterminate problems, again, they are over-constrained, and we have to look for additional information to assist in the static equilibrium. And again, by using static equilibrium is not enough. And what kind of additional information we're looking for, and the textbook gives this information. It's called a compatibility equation. We're looking for additional compatibility equations to help us with using this equation combined with the static equilibrium. That will be good enough to help to solve for all the problems. And this is the keywords, and the different type of the problem, they have a different type of the compatibility equations, and which is the essence you have to learn in these sections. Okay, and I will try to explain the things. The first one, we can work on the level problem we just did. For example, for this case, this is a rigid bar and won't deform, but remain as a straight line, will be tilted after the deformation of the fusings. So for this case, we want to calculate is the deflection of B, D, and E. Deflection, that means we simply want to calculate the movement of the movement of point B, D, and E. So in this case, it's likely the bar will be something like this. Okay, something like this, because we break down this. The two are elastic, so it could be like this. Okay, its intuition should be like this. So we simply want to know, for example, the displacement of point B like that, and displacement at point E at here. Okay, so for these questions, we can try is to use the let me use the small space of the board here. So for the problems I want to know is, the first one, I take the free-body diagram of this length AB, elastic, and CD, and the rigid bar. So that is a rigid bar here. And here is the loading we applied, 30 kilonewtons. And here is point B, here is point D. And for example, here, let me assume the force. Let me assume the reaction force here is FB, FD. And that is our assumed directions. For your exercise, actually, you can assume in either directions. Okay, either direction would work, as long as you keep all the calculation consistent with your assumption. And here is, I assume here. And on the other side, this is the AB. CD. And this is the point B, which means they use the pin to connect the bar to this bar, and this is a point B, point D here. So at the same locations, this simply to this is the action reaction. So once, if you assume the direction going up here, then here must be going downward, right? They have the same magnitude, the same thing here. Okay, so basically they have the same magnitude FB and P. And now we take the equilibrium. The first one is the force. We'll look at this problem here. The force equilibrium in one direction equal to 0. Then we will get is 30 equal to FB plus FD. And also, for example, we take the moment about the point B. This is point B equal to 0 on this. Then we will get is FD equal to 90 kilonewtons. So if we take a moment about this and taking into this dimension we given here, then FD equal to this. So therefore here we can solve for FB, and that is minus 60. So let me copy the information to here. FD equal to 90. And FB equal to minus 60. Because that's going to flood some people. So here you can see we calculate this in minus 60 upward.
Okay, so I assume.
So that means this will be equivalent is 60 pointing in this way. Okay, we try to get our calculation number as a positive. Okay, in this way we have to change the direction like this. Okay, so on this free body diagram, this is 90, and by force equilibrium, this is 90 here. By force equilibrium, this is 60 here. Okay, so these are 90 kilonewton, and this is 60. So from here you can see AB has been in compression. AB will get shortened. So that means if A here is fixed, B will move upward before we do the calculation. And D will get it downward. So that means here the B will be here, D will be here. And then, for example, if this will be original, let me copy it here. I'm kind of exaggerating the tilting of the bar. And this distance is delta B. The distance from here is delta D. And from here to here, that is delta E. And we can calculate delta B, delta D. Delta B that represents is the deformation of the AB. So simply we put into the PL over EA, this equation for AB. Okay, and P is 60 kilonewtons, and L is equal to 0.3 meters, and E equal to 70 times 10 to the 9th GPa, and 500 times 10 to the minus 6. And we simply do the calculation carefully with the unit. So basically this is 514 times 10 to the 6 meter. And this is the length, and Young's modulus and cross-section are given in the problem statement. And this one, keep in mind that is going up, so that means the displacement of point B is moving upward because the AB has been compressed. So A fixed, the B must go up. Delta D, the same thing, PL over EA, and for CD. Then we plug in all the information carefully. The answer is 300 times 10 to the minus 6 meter, and that is moving downward. So now how to calculate delta E. Let me erase this part for a moment. So here that is the original orientation of the bar, of the solid bar. And B is moving to here. Let me go here. So here is 1514, and the unit is 10 to the minus 6 meters, okay? And this unit is 300. And right now we're looking for this unit, delta E. And we have the dimensions here. From here to here is 0.2 meters, and from here to here, that is 0.4 meters. Are you able to use the similarity of the triangles to get this number? You should be. That is a high school math, I believe. Okay, and that is not the content of here. So here, if you do the thing, there's a many way to do this one. But again, using similarity of the triangles, you can use the two triangles, or you can use this triangle and the bigger triangles here. Either way, okay. So the answer should be equal to 1928 times 10 to the minus 6, and the unit is meter. Okay? The similarity of the triangles, that is the compatibility equation for this problem. Okay? Any questions? And here on the slide or in the textbook, we have the detailed calculations for that kind of similarity, and you can refer to the details here. Okay, and that even from the textbook should be available. And now we fix this one. The next one, I'm going to talk about this case. In this case, we can directly work on here. Because here we only have the doors at the front. If you want to go take a drink or go to your bathroom quickly, just go, okay, and don't feel weird or afraid. Just I don't have pass. I don't have pass to give that to you. So just feel free. For this problem, let me readdress. And here we have a loading. In general, the loading wouldn't be at the center, so let me put a little bit upward here. The magnitude is equal to P. And for this material, assuming that is uniform, so we have the Young's modulus, we have the length L, and we have the cross-sectional area A. Okay, assuming this material is uniform just for simplicity. So for example, we might be interested in calculating. You can see this is elastic bar, and we try to pull down from the middle. So at the top and at the bottom, they were both under certain reaction of unknown magnitude yet, right? So for this case, how can we do? There's a few strategies. The first one is this. For these problems, at this moment, I would need you to use a little bit imagination. This problem is this. For example, if there would have no constraint here, then the problem would be something like this. So this is the original length. And due to applications of the loading P here, then this end will be stretched a little bit. Okay, I use dashed line because this is the virtual, I need your imagination. However, this is the ground. Such an elongation is not allowed. So that means once this material is under loading, this point, material point at this end, has been trying to push the ground and trying to get the elongation like this. However, the ground preventing that from happening. So actually, in the real case, is this. This material virtually should be elongated by that much. However, reactions produced from the ground were preventing from that happening. So let me use the symbol. The arrow with the kind of the hyphen here is kind of the reaction. So such a reaction, let me call the RB, which is unknown. This RB is trying to push back the whole force by that much.